So notice that a Sierpinski space is indeed the smallest non-trivial connected space as it is a two-point set with either the particular point topology or the excluded point topology. And we have demonstrated previously that for a set with a cardinality greater than or equal to 2, then the particular point topology and the excluded point topology are distinct from the indiscrete or trivial topology. And in either topology, a Sierpinski space has one cluster point and one isolated point. So next we'll look at the discrete space. Let X be a countable set. And let tau sub d be the power set of X. That is the discrete topology on the set X. Then every non-empty proper subset U of X is both open and closed, and hence a discrete space is completely disconnected. All right, so now a new definition. A topological space X for which there exists an open neighborhood for at least one point in each pair, and we'll call those X sub 1 and X sub 2, in each pair of distinct points that does not contain the other. Such a space is called a T0 or Kolmogorov space. That is for every pair of distinct points x of 1 not equal to x of 2 in the space X, there exists open neighborhoods u sub 1 of the point x of 1 and u sub 2 of the point x of 2 such that either the point x of 1 is not in the neighborhood u sub 2 or the point x of 2 is not in the neighborhood u sub 1 of the point x of 1. A topological space X for which there exists open neighborhoods of both points in each pair of distinct points not containing the other, is called a T1 or Frechet space. That is, for every pair of distinct points x of 1 not equal to x of 2 in the space, there exists open neighborhoods u sub 1 of the point x of 1 and u sub 2 of the point x of 2 such that x of 1 is not in the neighborhood u sub 2 and x of 2 is not in the neighborhood u sub 1. So notice that not every T0 space is T1. However, every T1 space is T0. And the contrapositive is also true. That is, well, let me state it, the contrapositive that is, if a space is not T0, then it is not T1. Okay, so let's look at an example. Let tau sub p be the union of the set containing the empty set together with all subsets of the set X such that the point P is in that subset U. Then this is the particular point topology on the set X. Notice that every open set contains the point P, so there does not exist an open neighborhood of a point X which is distinct from the point P, an open neighborhood U of a point X distinct from the point P in the space such that the point P is not in that neighborhood, and hence the space is not T1. However, for every pair of distinct points, x of 1 and x of 2, both of which are distinct from the point P, the 2-point set containing the point x of 1 and P is an open neighborhood of the point x of 1 that does not contain or not containing the point x of 2, and the 2-point set containing x of 2 and P is an open neighborhood of the point x of 2 not containing the point x of 1. Further, for every point x that is distinct from the point P, the singleton containing the point P is an open neighborhood of the point P not containing the point x. And so for every pair of distinct points in this space, at least one of those points has an open neighborhood not containing the other. And hence, the space X is T0, or Kolmogorov. Okay, so there exists a very simple test to determine whether or not a given space is T1, or Fréchet, and so we'll state that now as a theorem. A topological space X is T1, or Fréchet, if and only if every singleton set is closed. So proof. Suppose that the space X is T1. Then for every pair of points, X and Y, that are distinct in this set X, there exists an open neighborhood of the point Y. Let's call that neighborhood U sub Y, of the point Y, such that the point X is not in this neighborhood. So let the collection U sub I, for I in the indexing set I, be the collection of all open neighborhoods of all points Y not equal to X, that is, all points Y in the set of the space set minus the singleton containing that point X. Then again, let this collection be the collection of all open neighborhoods of all points Y distinct from the point X in the space, such that the point X is not in the neighborhood U sub I. Then the arbitrary union of these neighborhoods is open, as it is a union of open sets. Further, this union is the complement of the singleton containing the point X, and as the complement of the singleton is an open set, we have that singleton is closed. Now this is true for every point in the space, and hence every singleton set is closed. So conversely, suppose that all singleton sets are closed. Let the points x and y be points in the space X such that x is not equal to y. Then X set minus the singleton containing the point y is an open neighborhood of the point X not containing the point Y, and the complement of the singleton containing the point X is an open neighborhood of the point Y not containing the point X. Now this is true for every distinct pair of points x and y in the space X, and hence the space X is T1, or Fréchet. So let's apply this theorem. So let tau sub E be the set, which is the union of the set containing the set X, together with all subsets of the set X, such that the point P is not in that subset. And this is the excluded point topology on the set X. So notice that for every point X distinct from the point P in the space, the singleton containing that point is open but not closed, and hence the space X is not T1. So as an exercise, show that a topological space is topological space with the excluded point topology. Is T0, or Kolmogorov. And we'll give the solution in the next lecture. So next example, let tau sub I be the set which contains the empty set and the set X, that is the indiscrete or trivial topology on the set X. Notice that for every point in the space, the only open neighborhood of the point X is the entire space, and so there does not exist an open neighborhood which does not contain or not containing any given point and hence the space X, that is an indiscrete space, is not T0.